Welcome to the 7th pre-recording of the Programming Languages Virtual Meetup. My name is Connor Hoekstra, and in this video today we are going to be covering the third part of Chapter 2 from the Structure and Interpretation of Computer Programs. So the table of contents for this part of this chapter is entitled Symbolic Data, and it has 4 subsections, 2.3.1 on quotation, and then 3 subsections that follow that are all example based. So the first one is on symbolic differentiation, the second one is on representing sets, and the final one is on Huffman encoding trees. What's interesting to note is that the first section that introduces quotation is only 5 pages long, and then the preceding 3 sections, you can't see it, but Huffman encoding trees goes to page 229, I believe. Makes up the remainder of the chapter, which is roughly 30 pages. So it very briefly introduces quotation and then hops straight into examples. So that's what we're also going to do in this video. So the textbook states all the compound data objects we have used so far were constructed ultimately from numbers. In this section, we extend the representational capability of our language by introducing the ability to work with arbitrary symbols as data. And it goes on to show this example where previously we were just defining our variables to be numbers. Now we are introducing the ability to define our variables to be symbols or to have lists of symbols. And we do this with a single quotation. So you can see here we have list AB, this prints out AB, and we can also have list quote A and then B without a quote. And this B here is referring to the variable 2. So pretty straightforward. The book or the textbook then goes on to state quotation also allows us to type in compound objects using the conventional printed representation for lists. And there's a footnote that talks about how quotation is a very confusing and powerful concept. The footnote reads, allowing quotation in a language wreaks havoc with the ability to reason about the language in simple terms because it destroys the notion that equals can be substituted for equals. For example, 3 is 1 plus 2, but the word in quotes 3 is not the phrase in quotes 1 plus 2. Quotation is powerful because it gives us a way to build expressions that manipulate other expressions, as we will see when we write an interpreter in Chapter 4. But allowing statements in a language that talk about other statements in that language makes it very difficult to maintain any coherent principle of what equals can be substitute for equals should mean. For example, if we know that the evening star is the morning star, then from the statement the evening star is Venus, we can deduce the morning star is Venus. However, given that John knows that the evening star is Venus, we cannot infer John knows that the morning star is Venus. So it's just highlighting that quotation. It's a very powerful thing we're introducing, but it leads to complications, which we should be aware of, and we're going to address later on in the book. So this brings us to our first exercise 2.54. It states 2 lists are said to be equal ? If they contain equal elements arranged in the same order. For example, equal quote this is a list with quote this is a list is true, but equal ? Quote this is a list quote this is, and then in sub parentheses is a end parentheses lists are not. To be more precise, we can define equal ? recursively in terms of the basic EQ ? Equality of symbols by saying that A and B are equal if they are both symbols and the symbols are equal, or if they are both lists such that car A is equal to car B and cooter A is equal to cooter B. Using this idea, implement equal ? as a procedure. So basically, this long-winded question is just asking us to implement the equal ? procedure recursively in terms of EQ ? And so here is my solution. We're defining our procedure equal ? that takes 2 lists A and B, and then we have our conditional expression cond. In our first clause, we're checking if both of A and B are null. If this is the case, we return true because 2 empty lists are true. This is also one of our base cases. Our next clause checks if either of A and B are null, which means that we've gotten to the end of one of the lists but not the others, which means they have different lengths. Therefore, we are going to return false. Otherwise, we check are the first elements of the 2 lists equal using the EQ ? procedure. And if so, we are going to continue to recursively make calls to equal question mark and cutter down both A and B. Otherwise, we return false, because if the two elements at the front of our list are not equal, obviously the lists in total are not equal. And you can see here I have started to use the racket unit testing module, so we can make calls to check equal to see that 0, 1, 2 is equal to range 3, which will give us 0, 1, 2, but 0, 1, 2 is not equal to range 2, which only gives us 0, 1. And this brings us to the first example and the second subsection of chapter 2.3. And this subsection focuses on symbolic differentiation. In all honesty, I was not a huge fan of this example. I preferred the second example on representing sets. However, the MIT lecture that Gerald Sussman, he focuses on symbolic differentiation. So they only present one of the examples, and they choose to focus on symbolic differentiation in the course. And that lecture is actually quite good. So I recommend watching the MIT lecture if you weren't a big fan of the symbolic differentiation subsection of chapter 2.3. But jumping into things, it basically introduces you to what you would have learned in Calculus 1 if you took that either in high school, depending on your program, or in university. These are basically just the rules for derivation. I'm not going to go through them because this is not a calculus course, and this is basically why I wasn't a big fan of it, is that if you haven't taken calculus, this is going to be quite imposing, and it basically requires prerequisite understanding of these derivation rules. But here they are. And then the book goes on to define a ton of selectors and constructors, and basically these predicate procedures, checking to see if what you have is equal to a sum or a product or a variable. I'm not going to go through this in depth. The key thing to note here, though, is that for our predicate procedures that are checking what's what, and for our constructors, note that the predicates are all operating basically on the first element of our list. So for sums, it's trying to identify that we have a plus at the front of our expression. And for products, it's trying to identify if we have asterisks at the front of our expression. And using that, it's going to basically be able to do dispatch and invoke the correct derivation procedure or formula in order to derive whatever the expression is that's being passed to our deriv procedure, which is shown on the next slide here. So then the book presents us with this. This is not something I've coded. This is what the book provides us with. We have a procedure called deriv, which is short, obviously, for derivation. And we have the expression that we're going to be performing the derivation on, and then the variable that we're going to be performing the differentiation with respect to. So once again, if you're not familiar with Calculus 1 or derivation, I apologize. But yes, hopefully everyone that's watching this has at least some familiarity with it, so they're not completely confused. And then once we have this set up, we're basically just doing a conditional expression where our dispatch happens. So if we have a constant, a number, this is always going to derive down to 0. If we have a variable, we're checking to see, is this variable the same as the variable that we are performing our derivation with respect to? If so, we provide a 1, else we provide a 0. And then we have two clauses for checking whether we have a sum or a product expression, and if so, dispatching to the correct derivations for each of those. And otherwise, because this is not a full-blown derivation procedure, you will return an error saying, don't know how to derive for the expression that you provided. So if you are familiar with calculus, it actually isn't too bad to understand. And what is impressive about this example is that very simply, we've sort of skipped, we're a chapter and a half into this book, and now we've coded a non-trivial, essentially derivation calculator for a certain subset of the possible expressions, which is quite impressive. This brings us to our next exercise, exercise 2.56, show how to extend the basic differentiator to handle more kinds of expressions. For instance, implement the differentiation rule of the following. This is when you have exponents. by adding a new clause to the deriv program and defining appropriate procedures exponentiation question mark, base, exponent, and make exponentiation. So base and exponent will be the selectors, make exponentiation will be the constructor, and the exponentiation question mark will be the predicate to check whether the expression we have is an exponentiation expression. It says you may use the symbol star to denote exponentiation. I actually didn't read that, and I used the hat, the caret character to represent exponentiation. This is what they believe they use in Python and several languages, but caret is typically used more often when typing. And it also states, build in the rules that anything raised to the power of 0 is 1, and anything raised to the power of 1 is the thing itself. So this is highlighting that previously in this subsection of chapter 2.3, it points out that there are times where we need to do reductions, similar to when we had the rational numbers example in either the first or second video that I covered in the structure interpretation of programs. Here it's also pointing out that we want to do some reductions in our constructor as well. So this is the predicate, the selectors, and the constructor. The constructor make exponentiation is on top here, taking a base and exponent, what we would expect. And then we have a conditional expression using the cond keyword with 4 different clauses. The first 3 are the special cases. So if the base is equal to 1, just return 1. If the exponent is equal to 1, just return the base. And if the exponent is equal to 0, just return 1, because anything to the power of 0 is just 1. Otherwise, we construct our exponentiation basically expression by creating a list that starts with the caret or the hat and then provides the base and the exponent. For our selectors, we can just basically redefine base and exponent to cadder and cadatter, and that's because base, we want to access the second element, which is going to be first a cudder and then a car, so you always read from the back to the front. So cudder, the D is for the first cudder and the A is for the last car. And then for the exponent, we want the last element, which is going to be 2 cudders, so cudder, and then car of just the last exponent here. And last but not least, we have our predicate function exponentiation question mark, which is checking to see whether the expression that we have matches the exponentiation expression that we would expect. And that's by basically checking that we have a list and that the first element of our list is this caret. So pretty straightforward if we're just following the pattern of what the book has given us so far. And once we have our predicate, selectors, and constructor, we can then very easily, so this looks complicated, but all we've done here is we've taken the book's example and then we've inserted our additional clause here for the exponentiation derivation. So here we're doing our dispatch by using our predicate function, so checking, is the expression that we're currently trying to perform differentiation on, does it match the exponentiation pattern, which is basically that caret? And then we are invoking the following if we meet the exponentiation predicate, which is to call make product twice. So the first one is to combine another make product, which is the exponent that we had, and then call to make exponentiation of the base with the exponent, and then a make sum of the exponent minus 1. So we're making calls to basically selectors here, base and exponent, to get the exponent from our original expression. So this is actually a bit confusing because there should be an R after some of these, because I'm basically confusing it because we have both the exponent and the expression here. So this doesn't stand for exponent, this stands for expression because it comes from the top level here. So yeah, probably I should have reformatted the book's example so that this isn't confusing. This should be really EXPR. So whenever you see exponent EXP, this actually means exponent of the expression, which is going to give us back the exponent because this is a selector. So back to what we were talking about, we're calling our make exponentiation constructor by calling the 2 selectors inside here to get the exponent and the base. So we're using the base at the bottom and the exponent minus 1. And then once we have this, we're using that as the first argument to our outer make product, which is then combining with the derivation of the following. And so this matches, if we scroll back a couple, this matches basically, so the deriv is what you see at the end here, and then the n u to the n minus 1, that's what you see in the inner make product. So this is the inner make product combined with the call to deriv on the base exp n var. And we have a unit test at the bottom here where we are performing derivation on x cubed with respect to x, and that's going to drop down the exponent in the front and reduce the exponent by 1. So we end up with 3x squared, which is what we expect. At this point, we jump to the second example, which in my opinion was much more approachable and didn't require any prerequisite knowledge of some university course that you may or may not have taken. And this was 2.3.3 representing sets. So basically this was different examples, starting off with the most naive of how to represent a set of unique numbers. So they had 2 or 3 or 4 different procedures that they defined for a different number of implementations. The first one was element of set. So does a number x exist in your current set? And the definition that they give is using a conditional expression, and they're saying if your set is empty, obviously it's false. Otherwise, if your x is equal to the first element of your set, then return true. Otherwise, recurse down until you either end up with an empty set and you weren't able to find a match, or you were able to find a match and you returned true. The next procedure that they go on to define is a join set, and that's basically just adding the element to the set if it doesn't already exist. So we just have a single if expression here. In the predicate, we check, does the element exist in our set? If so, just return the set. Otherwise, in the alternate, cons it to the front of the set. And the third procedure that they go on to define is intersection, which is basically given 2 sets, which elements show up in both. So here in our conditional expression, we're checking are either of these sets null. That's our base condition, or potentially you might have started off that way. If that's the case, if you have an empty set, then you have no elements that are in both sets because you have no elements in one of the sets. Otherwise, if you have an element, you make a call to element of set for the first element in set 1 and set 2. If this is the case, then you want to cons this element because it exists in both, and then make a recursive call to intersection set. Otherwise, if your element that you're currently at doesn't exist in the other set, then you don't want to include this and you just want to move on, drop that element, and then make your recursive call to intersection set and then cutter down set 1. So pretty straightforward. These are just the naive implementations. So the first question or exercise that we're going to look at from this this example is exercise 251, and it says implement the union set operation for the unordered list representation of sets. So union, as opposed to intersection, is the combined 2 sets without duplicates. So sets are only containing unique numbers. So for the intersection example, if we had set A equal to 1, 2, 3 and set B equal to 4, 5, 6, the intersection of that is nothing because there's no elements that overlap. But the union is all of them. It's the numbers 1 to 6 because you want to include all of them. So I re-implemented element of set just to make sure I knew what was going on, and got that working. But the solution to this exercise is on the bottom half of this screen. So basically, very, very similar to the intersection set. We're checking is null B, otherwise just return A. So we're going to be slowly, one by one, either adding the elements from B to A, or not adding them if they already exist. So we're doing this check again, once again. Is the first element of B in A? If so, drop that element, don't add it to A because it already exists. Otherwise, once again, make a recursive call to union set, cons the first element of B and add it to A, and then cutter down B. So based on the only differences between intersection and union are whether we're looking if they're in both or if they're in one. And then we have the same sort of pattern of in both the consequent and alternative clauses of our if expression, or I guess not an if expression. So in the last two clauses of our conditional expression, we're recursing down our respective function and then cuttering down one of the sets. And here we have two tests. Note that the pattern is a bit confusing. So for unioning 1, 2, and 3, and 4, 5, and 6, we end up with 4, 5, and 6 at the beginning of our list and reversed because of the way that cons works. And same thing with 1, 2, 3, 2, 3, 4. Note that 2 and 3 already exist, so we didn't end up appending that or consing it to the front, but 4 we needed to cons to the front. And at this point in this subsection, 2.3.3, it goes from the naive implementations to two alternative implementations. So the first one they talk about is if you have your elements in sorted order. And the second example is if you represent your elements as a binary tree. So the first one we're going to look at is the ordered lists. So here is the revised implementation of element of set, given that we have a sorted list of numbers. And the only difference here is that we're able to short circuit, meaning that we don't need to recurse down all of the elements of our lists if we hit the following clause in our conditional expression. So if our element that we're looking for is less than the current element, the first element of our remaining list, so if we've gotten to a point where we're looking at a value that is greater than our current element, we know that there's no way we're going to find that element now because it's in sorted order. So if we're looking for 4 and we reach the value 5, we know that all of the values after 5 are going to be greater than 5, and therefore we know that our value x doesn't exist in this list. So that at this point we can just check this clause, and if it returns true, then we can return false from our overall. Whereas previously we had to check every element because we weren't sure. Potentially the very last element was equal to our element that we were searching for. In this case, we know that after a certain condition, we can just return false. And then we go to their implementation of intersection set. This one's pretty interesting. Basically, it has the first same sort of clauses, checking whether either of them are null, and then returning the empty list otherwise. It does some bindings, x1 to the first element of set 1, and x2 to the first element of set 2. If they're equal, you cons this element, and then recursively work your way down the set 1 and set 2 by calling cutter and your recursive call to intersection set. Otherwise, you check to see which element is the smaller element. If it is the case that x1 is smaller than x2, you cutter down set 1, but you don't cutter down set 2, and then vice versa, because you want to keep these in sorted order, and this is what you need to do in order to maintain that property of your set. And this brings us to the next exercise, exercise 2.62, give a linear implementation of union set for sets represented as ordered lists. So I went a different direction with my solution. Instead of doing something recursive, I did something iterative. So the bottom half of the screen is just unit tests, which we'll talk about after we walk through our iterative solution to union sets. So union sets, taking two sets A and B, and then we're defining an intermediate iterative function that takes our two original sets A, B, and then our set that we will return C, and then we have a conditional expression. So if we hit the end of our list A, we then append the elements of B to our sort of accumulator set C, and we have to reverse this. I'll explain why later. Otherwise, if we hit the end of B, we do the same thing except for A, so we add the elements of A to C. Otherwise, we have these three clauses. So the first one is that if A if the first element of A is equal to the first element of B, then we cutter down both our sets A and B and then cons that element to C. The next condition is that A is less than B. If this is the case, we're going to cutter down A, add the first element of A to our accumulator. And the last case is where A is less than B or B is greater than A, the first elements of those two sets. In this case, we cutter down B and don't cutter down A, and then we append the first element of B to our accumulator C. So basically, we're always trying to put the smallest element into our accumulator set C. And in the case, and then when we add that element, we cutter down the respective lists. And in the case that they are the same element, we just add it from either A or B because they're the same, it doesn't matter, and then cutter down both of them. And then in order to kick this all off, we're returning from this procedure a call to iter A, B, and then our accumulator starts as the empty list. And note that we have a couple reverses here, which I said I'd come back to. So as we are consing up our sorted list, we're basically going to be reversing the elements that get consed. So we need to reverse what this iterative, how we kick off this iterative function or procedure call once we have all the results. But because we are also appending, append doesn't have this sort of inherent reverse in it. So we're going to end up with any elements that are left in A and B, they get tacked on to the end. Because of this reverse, they're going to end up reversed. So we basically need to add a reverse to the elements from B or A that we're tacking on such that we cancel out this reverse. So the append here necessitates a reverse to cancel out the reverse that we've added because we're using cons here. Maybe there's an easier way to do this, but this ends up working. And note that I have a bunch of unit tests to make sure that I got the behavior right. So we expect that regardless of the order that we pass 1, 2, 3, and 4, 5, and 6, that we always get back 1 to 6 sorted, and that regardless of the overlap or which list is shorter, we always end up with 1, 2, 3, 4 in order. And note that I was missing the reverses on my 2 clauses in my conditional expression before I added, I think it was the second unit test. So important always to have comprehensive unit tests. At this point, the section skips to implementing this sets in terms of binary trees. So this is the code that the book provides us with, a bunch of selectors and constructors, and then it goes on to define element of set, as we've saw twice before now, once in the naive implementation, the unordered version, and then once in the ordered version. And here it's basically the same thing that we've seen, but now because we have a tree representation, we have to traverse down the correct branches of our tree based on the value that we are searching for. So if we ever find our value, we return true. Otherwise, if it's less than our current entry, then we go left. If it's greater than our current entry, then we go right. Pretty self-explanatory. At this point, we come to a exercise 2.63, which states each of the following 2 procedures converts a binary tree to a list. So the first one is the following tree list 1. Given a tree, if it's null, just return an empty list. Otherwise, we're appending a recursive call to tree list 1 on our left branch, and then consing the current element we're at, and then making a recursive call to tree list 1 on our right branch. And here's the second implementation. This was originally called tree list 2 in the book, but I needed this for one of the follow-up exercises. So this one we're just referring to tree list 2. And this one is basically not recursive. The previous one was recursive and used append. This one is iterative. And the key here is that it uses cons. And the question goes on to ask, A, do the 2 procedures produce the same result for every tree? If not, how do they differ? What lists do the 2 procedures produce? I didn't write out the last one, but we'll answer the first one. And the second part says, do the 2 procedures have the same order of growth and the number of steps required to convert a balanced tree with n elements to a list? If not, which one grows more slowly? So the answer that I had to A was that they are the same. They're both in order traversal. We didn't look at the iterative solution as closely, but if you examine that, you'll see that we are adding the elements to the left, then the current element, then adding the elements to the right, which is in order traversal, as opposed to pre-order traversal or post-order traversal. And the answer to B is that the solution, the first solution, the recursive one, because it makes use of append, and append is a linear operation, we end up with steps or time complexity equal to n log n, versus the iterative solution that uses cons is going to be a linear solution. And just to highlight once again, so the cons in the iterative solution is here, the append in the recursive solution is here. And I believe this brings us to our final exercise of this example, which states using the results of exercise 2.63 and 2.64, which we didn't do, but we'll steal it from the book anyways, give a linear implementation of union set and intersection set for sets implemented as balanced binary trees. Note, I'm only going to cover union set as that's what I mentioned in the meetup. So intersection set to be left for a example for the reader or a watcher in this case. So the code that we need that was from 2.64 in order to answer 2.65 is the following. And this basically goes, so we had from tree to list. This goes from list to tree. So this is a rather complicated, or not complicated, but it's a non-trivial exercise. However, we have both tree to list and list to tree now. And given that, we can solve this problem in very few lines of code. So here is our union set. We are basically just, and this is very expensive in terms of memory, but it's what the book is asking us to do, is to make use of the two previous exercises. So first we convert so we read inside out. We read inside out. We convert our trees both into lists. So we have two sets, or I shouldn't say sets at this point. We have two binary trees representing sets, A and B. We convert these into lists, append them, remove the duplicates, and then just put this back into a balanced tree. And I didn't write a unit test for this one, but if we have the elements 1, 2, 3, 5, 7, 9, and 5, 6, 10, 11, 20, 23, 46, you'll note that we end up with a balanced tree. It's a little bit tricky to read, but 9 is sort of the root. And then all of these elements are on the left and all of these elements are on the right. And you can see that this is a balanced tree if you were to draw this out. And last but not least is our final section from this example. We're not going to go into too much detail. There's a lot in the book, and I encourage you, or hopefully you've read it before watching this video. But we're going to go sort of in broad strokes and cover this example. Huffman encoding trees. Basically, the book or the authors present an encoding. So if you've got 8 letters, A through H, you can encode them with the following codes. So 3 bits, 0s and 1s. And then if we want to encode a string, we basically just map. Anytime we have a B, you go put 001, which is the first 3. Anytime you have an A, you put 000. Pretty straightforward. And you're going to end up with 54 bits. The book goes on to say, though, however, if you have certain characters that show up a lot, so you can see that A shows up here a lot more than the other ones, and B quite a bit more as well, we can give these two encodings that are not prefixes of any of the other encodings. So A here is 0. Note that B through H, none of them start with 0, and B is 100. I guess this one is not, or yeah, so B is 100 and the remaining codes are all 4 bits. This is 3 bits. So none of these C, E, G, D, F, H, none of these start with 100 either. And if we do this and encode the same string that we had before, we end up with a much shorter string. So I don't know how many this is, but it is definitely less than 54. And the book goes on to show that this is quite a clever way to reduce the number of bits we need to encode strings, and it shows that we can basically construct this encoding using a Huffman encoding tree. And I'm not going to, like I said, go into too much detail here, but based on the number of times characters show up, you basically come up with this kind of set, and then you end up with this tree, and the way you get the codings is every time you go left, it's a 1, and every time you go right, it's a 0. And the letters that you are encoding only show up at the leaves of the tree. So A here would be 1, B would be 0, 1, 1, C would be 0, 1, 0, 1, etc. And so it's quite clever. And we're going to skip all of the code that the book introduces to exercise 2.67, which says define an encoding tree in a sample message given the following. So we've got A with 4, B with 2, and then D and C with 1. And then we have a sample message, which is the following, and it says using the decoding procedure, decode this message. So here is what this tree looks like. We have A directly off of the root, and then B is one level down, and then D and C are 2 levels down. So A is going to be 0, B is going to be 1, 0, D is going to be 1, 1, 0, and C is going to be 1, 1, 1 because it's right 3 times. And if we decode this, we basically just decode it in order. So 0, we go left, that gives us an A. Then we go back to the root, 1, we go right, 1, we go right, 0, we go left, and we get D. Then we're going back to the root, 0, we get A, and you get the procedures. So you're basically doing a single pass, recursing down your tree until you hit a letter. Every time you hit a letter, you go back to the top and continue to do it. And so you'll end up with ADA, BBCA if you do that. And this brings us to the final exercise that we are covering for the chapter, exercise 2.68, which states the encode procedure takes as arguments a message and a tree and produces a list of bits that gives the encoded message. And so we have the encode message as follows. It makes use of encode symbol. Encode symbol is a procedure which you must write that returns a list of bits that encodes a given symbol according to a given tree. You should design encode symbols so that it signals an error if the symbol is not in the tree at all. Test your procedure by encoding the result that you obtained in the previous exercise 2.67 with the sample tree and seeing whether it is the same as the original sample message. So basically we want to write a procedure encode symbol that, given a letter, produces the bits that are the encoding for that letter. So here is my solution. We have our procedure encode symbol that takes a symbol S and the corresponding tree. Right off the bat, we have an if expression, which in the predicate is checking whether we are at a leaf of the tree. If so, we have another if expression that's checking is our symbol S equal to the symbol that is at the leaf of this tree. If so, just return an empty list because we don't need to add anything to our encoding at this point. Otherwise, error out saying that we weren't able to match your symbol. Otherwise, we're doing in our consequent of our original if expression, our alternative of our original if expression, we're doing the following. So we're checking to see whether S exists in the symbols at the current branch, at the current node on the left branch of our tree that we're at right now. If that's the case, we're going left, which means we need to encode a 0. So we're consing 0 to our result, and then recursively calling encode symbol, passing it our symbol S, and then going down the left branch of our tree. Otherwise, we're going right, because it exists in our right branch, hopefully, unless we're going to error at the end. We're encoding a 1, and then recursing down, making a call to encode symbol, S, and then going down the right branch of our tree. So that will give us the corresponding encoding of ADA, BBCA, which, if you recall, is equal to what we saw in the previous exercise. So that is it for what we're covering from the textbook. At this point, I will make a few comments from the MIT lecture 3B, which covered the symbolic differentiation. The professor for this lecture was Sussman. And Sussman said, quotation is a very complex concept, and adding it to a language causes a great deal of troubles. So this was highlighted by the footnote that we read earlier in the textbook. He goes on to give this example, which is, in quotation, Chicago has 7 letters, and Chicago is the biggest city in Illinois. You know, according to logic, if you speak this, you would then think you could say the biggest city in Illinois has 7 letters, but this is not the case due to the quotations. So this is exactly what that footnote that we read earlier was highlighting, is that introducing quotations adds complexities. Gerald Sussman goes on to say we can't substitute into what is called referentially opaque context. So I highlight this because this is the first time I've heard the term referentially opaque. Obviously, we covered the term referentially transparent earlier in the book and compared that to pure. But this is the first time I'm hearing referentially opaque, and he's alluding to the fact that quotations, the use of quotations, necessarily introduces referential opaqueness, if that's a word. And last but not least, at this point, we've built our sledgehammer, is what Sussman says at the end of the lecture. And he says we have to be very careful because this is a very, very powerful thing that we've just introduced. We can now do type dispatch. We can now build, domain-specific languages, and we have to be careful, not to just start smashing fingers and toes because it's a very, very powerful feature that we've just added. And 2 pre-recordings ago, I showed this map, which is a history chart of early programming languages, ALGOL, COBOL, Fortran, and APL, all on this map. And I said that I was going to cover or do a little mini biography, as we've been doing in some of the videos, on Gene Samet, who is the person that created that wonderful program language history chart. So, who is Gene Samet? She is one of the members of the original COBOL group and was highly influential in that group in standardizing COBOL. She has a bachelor's in mathematics from Mount Holyoke, I'm potentially pronouncing that wrong, college, and then later got her master's in mathematics from the University of Illinois, I think it's Urbana-Champaign, and later she was awarded an honorary PhD from Holyoke College. She developed Formac, which stands for the Formula Manipulation Compiler, which was an extension to Fortran 4. So it was one of the first compilers for compiling formulas and doing manipulations with them. And it was, from what I read, more of actually a transpiler. It transpiled this code that was written in Formac to Fortran and then ran in Fortran. So I guess transpiler, compiler, what's the difference? And she did this while at IBM. She was the president of the ACM from 74 to 76. So the first president that we saw in this sort of mini biographies was Alan J. Perlis. And notably, she was the first female president. She's the author of the Programming Languages History and Fundamentals book, which I have on Amazon Delivery, which was supposed to be here in June, but it has not arrived yet. Hopefully it will soon. And last but not least, her first job was at MetLife, which is of interest to me because I started my career as an actuary. MetLife, as some of you might recognize, is the company that used to have Snoopy as its logo. It's an insurance company, but I guess they went through a rebranding campaign. I'm sure they spent millions on it. But yes, that was where she started her work. That's it for this week. I hope you've enjoyed and learned something. We'll be back next week with Chapter 2.4. Hope you have a great day, and we'll see you later.